thank you very much for attending this lecture of mine. I compliment you for sticking to the last lectures on the last day, and so you should be praised for that, and I appreciate it. I also wanted to thank Professor Kwan for and Professor Yun for the invitation to speak here at this workshop. I hope after I give this talk they don't regret the invitation. And it's very nice to see Professor Kwan again. It's been many, many years since the last time we met, you know. Also, I want to single out Professor Yun and also Dr. Youngju Lee for their tremendous effort on my part to arrange for an extended stay in Korea. They really worked very, very hard to deal with the administrative burden of getting me supported by this interesting program called the Brain Pool. Mm-hmm. So I'm a part of the, now I guess officially a part of the Brain Pool in Korea. So, and I do very much appreciate their efforts. It was quite a struggle, I would say, to go through all the details necessary. So I'm happy to say I'm going to be here in Seoul for, I think, at least 2 months, perhaps longer. We'll see what happens. I want to now tell you a little bit about this talk. I give this talk with a certain amount of trepidation because it's what would seem to be a very well-known standard sort of issue. I guess I've been aware of it, vaguely aware of it, implicitly aware of it for many, many years, this issue of approximating an ideal filter by a polynomial. So I really don't know much about this. You might wonder why I'm giving this talk. I do have something to say, and I'll get to it in a minute. Since I'm not really an expert on this issue, I would like you to think about my talk as not necessarily something that I take any prioritization for. I don't claim anything that's new or novel or unique to me and my collaborators. I view this as more informative. I hope that there are some things that I say that you're not aware of. Now, in fact, a few days ago, I had a conversation with my friend and colleague, Yi Sun, who said, "Oh, isn't this subject related to a paper I wrote?" So when we sort of exchanged some buzzwords, you know, he said something, I said something, and the conclusion is it's not. But we're not certainly sure, because I'm not quite aware of his paper and what he had to say. So we'll decide after I give the talk whether this is subsumed in one of your voluminous papers, right? When was the paper written? 2000 what? 2? 3. Okay. Well, actually, you know, when I got involved in this work, and I'm going to tell you how it developed, I did make an effort to check around here and there, so-called experts in EE about whether there was a literature that they knew about this subject, and I didn't turn up anything. So there's some potential that what I have to say this morning is in fact new under the sun and original to me and my co-authors. I'm very fortunate to have two very bright, hardworking, intelligent, creative co-workers. In fact, without these two guys, I think, let me see, without these two guys, I wouldn't have anything to say. This is Wang and Yi Wong, and I want to tell you a little bit about them. Yi Wong is from Chengdu. He now is in residence in America. He's an associate professor at Montgomery, the Auburn campus of Montgomery, Alabama. Montgomery is a very interesting place to go too, because when I first went there, he was kind enough to take me to Costco. It's the first time I went to Costco. And Costco is a very interesting place because you go in and they have these enormous hot dogs that you can buy for only $1, you know, and encourage people to go shopping there. In Korea, they cost twice as much. So, and there are other things to say about Montgomery. It's an interesting place. The first White House is in Montgomery. Now, the White House I've always thought was in Washington, D.C., but there's a White House in Montgomery that was initially occupied by Jefferson Davis just prior or in the beginning of the Civil War. It's a small, modest home, and he spent a few days, weeks, I don't remember, and then he moved his government to Richmond. So it's an interesting thing to see. But one of the biggest employers in Montgomery is Hyundai. Hyundai has an enormously big plant. So they're producing cars for American consumption. And in fact, Montgomery, the Auburn campus of Montgomery, is not the main campus of Auburn University. It's in Auburn, Alabama, which is about an hour by car from Montgomery. And I had occasion to visit that university some months ago. And I arrived at the Atlanta airport and I drove to Auburn. I'm driving along the highway and I see a big sign that says Home of Kia. So Kia has a big manufacturing plant in I guess it's Georgia. I couldn't figure out whether it was right over the border into Alabama. So we love Korean cars in America. You know, and 20 years ago you didn't see any Korean cars in America, but now they're really all over the place. And both Hyundai and Kia advertise aggressively on American TV. And I notice that there are some American cars on the road in Seoul, so that's a good sign. I see that Chevrolet is producing some cars, and I guess I've read that Korea and America have this free trade agreement, so hopefully there'll be more American cars on roads in Korea as time goes on. So that's, excuse me, Yi Wong. Yi Wong has 2 PhDs, one in double E, from Chengdu, and one in mathematics from a university in America. So Zhenzhou Wang is at Sam Houston State University near Houston. Now, a number of you know him, and he's just a great guy to be with because anytime you're in Zhenzhou's presence, he's always smiling. He's always a very happy guy, and he sort of lowers your blood pressure. You know, it's just a great pleasure to be around, and really an accomplished and a mathematician. So I'm very lucky to work with these two guys. So as I said, I don't know much about this subject, and I'm going to tell you the little bit I know before I finish my talk. So you have to be patient. So I want to tell you how I got started. It's sort of an interesting story. It's the way I do mathematics. You know, I don't sort of sit down and read a book, you know, from cover to cover and to try to check the proofs of all the theorems and memorize them. It's very difficult. Or read papers. It's really very hard. Unlike this phrase that's associated with Paul Erdős that says, you take coffee and you turn into mathematics. The way I've done it is I just sort of chat with people. The way I think about it is if I take people that are mathematically sensitive, I bring them to my office and I close the door, and then we just sit there and chat, then eventually mathematics comes from that experience. And this is the way this collaboration started many years ago. I think it must be about 4 years ago. I was in my office in Albany, and my colleague, a guy called Ki-Yu Sun, not Ki-Yu Sun, you're Ki-Yu Sun, Ki-Hei Zhu, excuse me, I see you right there and got confused. So Ki-Hei Kihei Zhu is my colleague. In fact, he's currently the chairman of the math department, a very nice guy, accomplished mathematician. He came into my office and said, would you like to host a visitor from Changsha, a graduate student, who is working with my friend from Changsha. I mean, Kihei Zhu originally came from Changsha. And this lady, graduate student, is from a military university in Changsha. I don't know the name of it, but there's some military university. So they do some secret hush-hush work for the Chinese military. I don't know. I know nothing about it. So, so I said, okay, fine. Then she came. But after she came, I discovered that she had been pursuing other alternatives beside coming to Albany. So, for example, her first choice was to go to Canada, to University of Alberta in Edmonton. That's really a nice place. I had many occasions to visit there and collaborate with people, not in recent years. So, but the Canadians refused her because she comes from a military university. You know, our northern neighbors is noted for their peaceful and tranquil point of view about life. I don't know, I'm not sure they have a military. They do, yeah. They have some volunteer military or so on. So I guess when I think of Canada, I think of an entitlement society. You know, everybody has health care and Social Security, pays high taxes, but not to support a military. On the other hand, you know, America spends a lot of money to support their military, and they're absolutely delighted to have military exchange with various peoples of the world, even with the Chinese. In fact, they seek it out. You know, our military have gone to China and vice versa, and so that wasn't a problem for this student to come to Albany. And a couple of days ago, I guess I was reminded of the fact that she also considered the possibility of working with Kyu Sun in Central Florida State, but somehow or other decided to come to Albany. So anyway, she came, and the first week or two, we began to get familiar with each other, and she came with a very big stack, well-organized stack of papers, all from various IEEE journals and publications. So I don't read IEEE journal and articles and know very little about what appears there. So I tried to encourage her to leave her focus, her subject that she seemed to want to work on, and she got a little bit upset. And so I said, oh, well, we have to, at least I have to, since I took responsibility for her, accept the fact that she wants to work on these articles that appeared in IEEE, and I don't know much about it. And so I look at these articles, and they were concerned with this issue, and they were, you know, they're relatively recently short articles about polynomial approximation to the ideal filter, and they were sort of couched in the terminology of wavelets, some sort of wavelet stuff as well. Not much mathematical analysis in these papers. You know, some offer of a method to generate polynomial approximation ideal filter, a couple of minor comments, and so I didn't know what to do, and I decided to create the following problem, which is totally useless, no practical application, is to ask what happens when the degree of the polynomial gets arbitrarily large. Now, nobody cares about filters with arbitrarily large degree polynomial, so it's a mathematics problem. And you know, we began to discuss the issue, and through that I became desperate to have dialogue with someone about it, because I was the leader of this research activity. So I then called up my friend Yi Wong, who has a degree in EE, and pleaded with him to be a part of this research, and so we moved forward, and he, with his hard work and creative energy, we prepared something. We got to a certain point, and then it must have been more than 2 years ago. And then I went to Hong Kong, to City U. And when I went to City U, they gave me a whole bunch of startup money, a lot of money. And also I had a grant, so I was able to invite a lot of friends. And one of them was Wang. He came, and just by chance, he saw this paper. And then he got interested in it. And then began to work, and then edit, and then we wrote this paper. And now you can find it online in Advances in Computational Mathematics. Eventually it'll appear in hard copy. So because the paper appears, I don't have to get into a lot of the details of it. So you're fortunate. I'm not going to prove anything or tell you about a lot of the stuff in that paper. If you want it, check online. I prefer giving talks like that. I prefer talking about things that have already appeared. So if you're interested, just go Advances in Computational Mathematics, look online, there's the paper, and you can see all the details that I failed to tell you about. So that's the background. Now I'm going to get to the transparencies. I want to say about the nature of this talk. It's useless, no practical application, no algorithms, no high dimensions. It's univariate. So that's from someone who spent 30 years in industry, okay? So no pictures, no black and white pictures of Lena, cameraman, baboon, no computation. It's just a couple of observations, mathematical observations, and that's it. So this is sort of the way I like to express myself scientifically. Sort of few mathematical facts and sort of bury the challenge and effort and headache and struggle to prove the theorems. So that's the nature of this talk that I'm going to give in a moment. I must say that the spectrum of talks given here is quite wide and very interesting, and I appreciate all your contributions, and I've learned a lot of things to think about. This is a mathematics talk with a couple of observations. So I think I'm ready to go to the first transparency. Let me see, get this right. There we go. So this is the problem. Now, let me see if I can keep this steady. This is an ideal filter. So here, ideal filter is 0 on some interval. The interval has been normalized as 0 to 1, but filter design usually takes place on the unit circle. You map it into the interval 0, 1. 0, 1 feels more comfortable. So here's it's 1, 0 here, and then it jumps up to 1, and then there's a transition interval here. This is called the stop band. See, S for stop band, and this is the pass band. This is the right-hand interval of what's called the transition band. The length of this interval in my transparency is called W. Okay, so stop band, pass band, transition band. Okay, and the oh, I'm glad you're asking a question already. What's I haven't even gotten started. Go to the board. What?
No, I just want to make sure. Polynomial, you mean trigonometric polynomial? Or?
No, algebraic. Everything is on the, we mapped everything, just make some transformation. This is polynomial, but we can put it back on the unit circle. Yeah, okay. So we avoid complex numbers. Keep it simple. Okay, so this is actually what you're looking at is an actual computation. This is not sort of just a stylized wiggly function. Yi Wong actually computed a polynomial approximation to this particular ideal filter. So let's see. So this is some polynomial, and the issue is, of course, this polynomial has to be close to 0 here and close to 1 there. So that's the challenge, to try to find such polynomials. But our interest is how well we can do this approximation. Okay? And in the sense that, we would measure an error here, some norm, maybe L infinity norm, L2 norm, and actually it doesn't matter really, because it's I measure the error here and measure the error there, and then I take the nth root of it. So I'm only considering nth root asymptotics. Now, nth root asymptotics is easy because the nth root of n is 1. So if you have algebraic growth, it doesn't interfere with nth root, so you can just throw it away. Okay, so it's easier to deal with nth root asymptotics. And so that's what I'm concerned about. Let's see, so stop band. In my next transparencies, I use the letter X, capital X sub S for stop band, and capital X sub P for pass band. And then I have this transition interval. And the question is, how do I produce a good polynomial approximation to the ideal filter? Any other questions? Okay, so let's see what happens next. So actually, let me go back to this. Let me go back to this picture. So I've been accused of being an approximation theorist. I don't really know a lot about approximation theory, but when I was young in graduate school and somewhat thereafter, I did read books on approximation. And unfortunately, Amos is not here. It would have been nice if I could sort of needle him a little bit because of his talk yesterday. The way people in approximation theory would approach this problem is use what is called Jackson's theorem. Jackson's theorem is presumably a constructive way to generate a polynomial. But there's a problem here because this function has a gap in it. There's some gap. So we don't know what happens here. So usually when you do Jackson's theorem, you have a function on this interval. And then you approximate it in some norm. Typically, the challenging norm in approximation theory is the L infinity norm. That's the way approximation theorists sharpen their teeth. It's very hard to approximate an L infinity norm. Okay, but I need to know this function here, this transition function. I don't know it. I only know the function is 0 here and 1 there. Okay, so let's keep that in mind because there are actually two approaches that we have for this problem. The first one is based on, what is this thing? Jackson's theorem. Now notice this version of the Jackson theorem is, this 2, not surprisingly, stands for the L2 norm on the interval 0, 1. Now, this is the first substantive transparency I have, and I notice there's an error on it. I realized this morning at 3 o'clock or 4 o'clock in the morning when I got up thinking about this stuff. Now, does anybody see where the error? Oh, no, I'm sorry. There's no error. I thought this was an F. So I compliment myself to say that this is accurate. So here's my ideal filter. Now, the ideal filter is assumed that I fill in the space between 0 and 1 by some function. Okay, I fill it in, and I approximate it in the L2. I choose L2 for a very specific reason because it's hard to do it in L infinity. And in fact, if I look in books on approximation theory, what they say is if my ideal filter, or indeed any function, has k derivatives, then the error decays like 1 over n to the k. See, n to the k, 1 over n to the k. Suppress the regularity, okay? But what's important in this bound is I know exactly how the constant depends on k, okay? There's a simple lemma in L2 which gives me the dependency on the Jackson theorem in terms of k. You prove this by using ultraspherical polynomials. So I now consider the following possibility. I'm going to fill in, let me go back to my, what is this? Let me go back to my ideal filter, and assume I filled in my transition from 0 to 1 by some function that has k derivatives. K is at my disposal. Remember, I'm interested in knowing how well I can approximate by a polynomial of degree n when n is large. So I pick a k, and I use this bound. Now notice, the derivative of 0 is 0. The derivative of 1 is also 0, as long as k is greater than or equal to 1. This k is greater than or equal to 1. Okay? So in this bound, I have the L2 norm on the transition band. I don't see what happens on the stop band. I don't see what happens on the pass band. So I have a couple of interesting quantities. I have k at my disposal. I have n, which is the degree of the polynomial. And I have this term. So what am I going to do? Well, I want this bound to be as best as possible. So I'm going to fill in the transition between 0 to 1 so that I minimize this quantity. Okay? Now, keep in mind, there's a constraint on the ideal filter. It must match 0 in the stop band up to order k. That imposes k 0 conditions at the right-hand endpoint of the stop band interval. And it must match to 1 on the pass band. So that means it must be 1, and all the derivatives as well are 0. So those two constraints, I then minimize this, and I see what I get. And let's see. So here's what we get. A little bit of effort. So I need an error criterion. I choose, again, L2 norm. So I look at the polynomial on the stop band, how close it is to 0, and I look at how close it is on the pass band to 1, and I minimize this quantity. This is a sort of non-traditional L2 minimization problem, because it's a sharing of two norms, one on the stop band, one on the pass band. I define this number epsilon 2n, depends on the length of the stop band and the length of the pass band. And I produce this bound. Okay? So now, at my disposal is n. I'm sorry, k. N is given. And I'm going to now minimize this over k. A little bit of effort. This gives me an upper bound. Okay? This is from the Jackson theorem. Now, what I want to explain to you is how I get a lower bound. Because I'm going to optimize over k for a given n. And I want to see how well that compares to a lower bound. So let's go to the lower bound argument. Before I tell you how I optimize this over k for a fixed n, w here, by the way, is the length of the transition band. Okay? So I'll explain later how I optimize this. So I go now to lower bound. This is upper bound. So upper bound, lower bound, I use Bernstein, just like Amos did yesterday. He had an upper bound, he called it Jackson, although I didn't recognize why he called it Jackson. And then he had a lower bound he called Bernstein. The Bernstein is convenient for a lower bound. So here's the technique of a lower bound. It's actually kind of nice. Here is the stop band, and here is the pass band. Okay? Now, my polynomial is close to 0 here. I have some bound on the polynomial. Any polynomial is supposed to be close to 0 there. And here is supposed to be close to 1. Okay? But this interval, stop band, and this interval, are separated. There's a gap. So how am I going to somehow deal with the fact that this polynomial is struggling to be close to 0 on the stop band, and then all of a sudden has to shoot up to 1? So I remember Bernstein. Bernstein says, as I learned a long, long time ago, if I have a bound on a polynomial on this interval, I can go into the complex plane, and I can extend it to an ellipse encompassing that interval. So I put an ellipse around this. And knowing a bound on this interval, I can start expanding that ellipse, and I likewise do it on this interval. and I expand it, and all of a sudden, these ellipses intersect. Now we have a problem, because the polynomial is much close to 0 here, and it's close to 1 there. And that's the way you get a lower bound. Now I'm going to make this precise with a formula. I need to know exactly what this point is. It's going to depend on the Bernstein ellipse for the stop band and the Bernstein ellipse for the pass band. So here's the formula. Simple lemma about polynomials is, if this is the stop band, then P, any polynomial, at this point x0, s over 1 minus w, is bounded in absolute value by this constant times the norm, L infinity norm, on the stop band. And likewise, 1 minus p at this number is bounded by the same thing, but now times the L infinity norm 1 minus the p. So I could put these together. Notice this plus this, by the triangle inequality, exceeds 1. Right? This plus this. So if I add these two together, I get a bound on this. I get a lower bound. Okay, so I have a technique for a lower bound, and I have a technique for an upper bound. I put them together, and I get a theorem. What happened here?
Sorry, for the two ellipses.
How do you make it bigger?
I have to go to the computer.
I shrunk it accidentally.
Let's start with the two ellipses. How do you, or you have the two ellipses, so one ellipse grows and the other grows at the same time? What's the...
Is it a mathematics question or about the...
No, on the ellipses.
Oh yeah, both ellipses are growing, and depending on the size of the ellipse, you get a bound on the polynomial in the complex plane.
How do you measure the size of the ellipse?
By some parameter. It has to do with the semi-major axis.
Because the ellipse, one ellipse can get bigger than the other ellipse, right?
Okay, this is the Bernstein inequality.
Oh.
You know the Bernstein inequality. Yeah, the details are in the paper. Okay. I mean, it's hard to think when I'm standing here. Okay, so now here's the bound. Now look at this. This is a nice function. 1 minus the square root over 1 plus the square root. This is lim in lim sup. So I don't nth root. Here I don't assert that the nth root goes to a limit. I just say lim nth is less than lim sup. And amazingly on the top appears what's called the Lambert function. It's the first time in my life I've ever encountered. Did you ever encounter the Lambert function? Often?
In functional magnetic resonance imaging.
I'm sorry, say that again?
In functional magnetic resonance imaging.
Really?
I've used it.
Well, the first time I've ever encountered the Lambert function. So here's the Lambert function. It's the inverse of the function t e to the t. Okay? Actually, I processed a paper for advances in computational mathematics about the Lambert function. So here's a bound. So lower bound, upper bound. So now what we do some computation to test whether this is good. Turns out it's lousy. The picture is just lousy. This one is really lousy. Now pay attention to this lower bound. Now, all of this has to do with filling in this in an optimal way the transition. Is all no good. We're going to change new approach to solve this problem. We impose on the polynomial a simple condition called half band. Now, half band is very natural. You want this polynomial to be small on the stop band. So if it satisfies this, it's close to 1 on the pass band, right? As long as the length of the stop band and pass band are the same. Everything is nice, symmetric about. So now, all we got to do is worry about the stop band. The pass band is already taken care of. We don't care about any transition. So we have a problem now. Our filter, our polynomial filter, satisfies this, and we got to sort of deal with this equation. And we look and say, if P is a half-band filter of degree n, n must be odd. So half-band filters are odd, and we demand the length of stop band and pass band are equal. Before we didn't. In fact, if we differentiate this, then P prime of y plus P prime of 1 p prime of y minus p prime of 1 minus is 0. So the derivative is symmetric about a half, and we use all of this fact, and we struggle with this half band, and then we prove a theorem. Oh, before we prove a theorem, we need to know some notation. So I said that we only have to look at the stop band, and we only have to look at the L infinity norm. Well, L2 norm is okay too, because it doesn't matter what norm we look at since we're dealing with polynomials. And we now introduce a new idea, is that we're going to make the polynomial, which satisfies the half band condition, have an L fold 0 at 0. So it's going to touch the 0 polynomial in the stop band with a prescribed 0 at L. That's a good thing from signal processing point of view. Isn't that right? Okay, so we imposed that additional condition. Before I didn't. Okay, so we have this problem now. Notice this is an infinity rather than 2, but it doesn't really matter. So we minimize the L infinity norm on the stop band amongst all polynomials that satisfy the half band condition and have a L fold 0 at 0. And now I'm getting close to the end of this talk. So here's the theorem. I have to read this for you and remind myself what it says. So n is an odd integer because that's the degree of welcome. Come, we have a seat for you. Yeah. I'm surprised you're here. I mean, you had to run from your hotel. I hear your hotel is in a remote location of Seoul.
Charlie, in order to attend your talk, I woke up 1 hour early.
I see. Well, I'm glad you're here because I want to talk about you. But I mean, at the end of the talk, I only have 5 minutes, and I need at least 20 minutes to say something about you. Yeah. But anyway, you're right in time for the main theorem of this show. Here's the theorem. N is an odd integer. L is the order of contact of the polynomial at 0. Now notice, I allow it to depend on the degree of the polynomial. Okay? It's not fixed independent. It's growing with the degree. And I have it growing as ln over n. So it could be independent, in which case that theta is 0. So this theorem doesn't cover that case, which is the case I covered when I did the optimal fill-in. Okay? So here's the result. The nth root of this goes to a limit. It depends on theta, the growth of the 0 at 0, and it depends on the length of the transition band. So now the question is, what is f? So here's f. This is very exciting. That's the function. So I'll read it with you. Square root of 1 minus w squared, 1 minus theta squared to the 1 minus theta times the quantity, and so on and so forth. So I'm about to end this talk. Thank you for arriving at the end, Amos. I appreciate it. But I know you're going to have a question. And I give you a hint as to what question to ask. Ask me how that is...
Why does it look so complicated?
I don't know. Truth is... mathematical truth is that way sometimes, But you can ask me how that's proved. Let me see.
That is a trap. If I ask you how this is true, you will show us the problem.
Let me remind you of the theorem. The theorem is this, okay? By the way, for your sake, let me move forward. For Amos's sake, this is an S, is fixed, okay? And watch this quantity. See this quantity here? I'm going to define it for you. Here it is. It's just the minimum of a polynomial. It's the minimum of in the L infinity norm on the interval 0 to S. And that polynomial satisfies, this is for Amos's sake, this condition, which is called the half-band polynomial condition. And the polynomial has an L fold 0 at 0. So we look at that thing, and then the nth root goes to this thing, and that thing is that. And so that's it. So anybody have any question, Amos? Thank you very much.